This is one of the earliest data models, used in systems like IBM's IMS in the 1960s. In a hierarchical model, data is organized in a tree-like structure. 7. Records have a parent-child relationship. Each record, except the root, has exactly one parent, and it can have multiple children, much like an organizational chart or a family tree. For example, a hierarchy might represent a company's org chart. A department record is parent to employee records. Each employee might be parent to dependents records, etc. The structure is rigid. One-to-many relationships are easy. Each parent can have many children, but many-to-many relationships are not directly supported. Hierarchical databases excel at fast one-to-many data retrieval but can be less flexible. They require navigating from the root down through the tree to find data. Network data model. The network model, formalized by CODASYL in late 1960s, was an extension of the hierarchical model. It allows a record to have multiple parents, essentially supporting many-to-many relationships natively. 8, 9. Data is organized as a graph, or interconnected network, of records. In the network model, records are called nodes and relationships are called sets. A record can be a member of multiple sets, meaning, for example, an employee could belong to multiple projects, each project and employee being a record, with a works underscore on set linking them. This model was more flexible than hierarchical, but still required programmers to navigate pointers between records. Both hierarchical and network models are called navigational databases, because you navigate through linked records. Relational data model. Introduced by E.F. Codd in 1970. This model is the foundation of modern RDBMS, relational database management systems. The relational model organizes data into tables, relations, consisting of rows and columns. 10. Each table represents an entity type, e.g., employees, departments, and each column in the table is an attribute describing that entity. Each row, tuple, in a table is one record instance of the entity, uniquely identified by a primary key. Relationships between entities are represented by storing primary keys of one table as foreign keys in another. For example, an orders table might have a foreign key column customer ID that links each order to a row in a customer's table. This model is declarative. You can query data using high-level languages, like SQL, without specifying the navigation path. One key aspect is that it supports set-based operations. You can join tables, filter, group, etc. using mathematical set logic and relational algebra. The relational model also enforces integrity constraints, like maintaining referential integrity between tables. Because of its simplicity and power, tables with keys and set operations, the relational model became extremely popular and is still widely used today. 11, 10. Object-oriented data model. As software development embraced object-oriented programming, OOP, in the 80s and 90s, databases followed suit with object-oriented databases, OODBMS. In an object-oriented model, data is stored as objects, similar to how programming languages like Java or C++ represent data. These objects include both the data, attributes, and the behaviors, methods. The model supports complex data types, inheritance, and relationships as references between objects. 12. For example, you might have a customer object that contains an array of order objects directly. UDBMs aim to address the so-called impedance mismatch between relational databases and OOP by storing data in a format closer to how applications use it. However, object databases never became as widespread as relational ones, partly due to standardization and performance issues. NoSQL and other models. Beyond the classical models, modern data needs have spurred new models, often grouped under the umbrella of NoSQL, meaning not only SQL. These include document databases, which store semi-structured data like JSON documents, e.g., MongoDB, key value stores, which store very simple key equals value pair data, e.g., Redis, wide column stores, like Cassandra or HBase, which use a sparse tabular structure optimized for big data, and graph databases, which excel at data with complex relationships, like social networks, using nodes and edges. In a sense, these can be seen as variations or extensions of earlier models. For instance, a document model can be thought of as hierarchical. Documents may contain sub-documents, but with more flexibility. A graph model is an extension of the network model with explicit support for any-to-any links. 13, 14. Each of these models has its use cases. Key value and document stores are great for scalability and flexible schemas. Graph DBs are great for relationship-heavy queries, like shortest path, network analysis, etc. We will talk more about SQL versus NoSQL shortly. In practice, when designing a database, the data model you choose dictates how you conceptualize the data. The relational model remains dominant for structured business data due to its balance of simplicity and rigor. High-level conceptual models like the entity relationship model are also used during design. In an model, we draw entities, attributes, and relationships, which can then be mapped to a particular data model, usually relational. The model is a way to design databases conceptually, often mapping to a relational schema, tables, later, 15, 16. In summary, understanding data models is important because it gives us insight into how data is stored under the hood, which impacts how we write queries and how the system performs. Transition. Now that we know different ways data can be modeled, we turn to the language that unlocked the power of the relational model, SQL. SQL Introduction. SQL, Structured Query Language, is the standard language used to communicate with relational databases. It was developed in the 1970s alongside the relational model, initially called SQL, at IBM. SQL allows us to create, read, update, and delete data in a declarative way. But what exactly is SQL? Formally, SQL is a programming language that lets both technical and non-technical users query, manipulate, and manage data in a relational database system. 17. SQL is often described as declarative because you specify what data you want, not how to get it. The DBMS query optimizer figures out the best way to retrieve it. In SQL, data is organized into tables, as per the relational model. Each table's columns have defined data types. We'll cover data types more in the next script, and tables can be linked by keys. SQL has several sublanguages or categories of commands. DDL, Data Definition Language, commands like create table, alter table, drop table. These define or alter the structure of the database. DML, Data Manipulation Language, commands like insert, update, delete, for modifying the data itself. DQL, Data Query Language. The primary example is select, used to retrieve data. Some people include select under DML, but it's often singled out as querying. DCL, Data Control Language, commands like grant and revoke, for controlling access, permissions. We'll talk about DCL in script 5. TCL, Transaction Control Language, commands like commit and rollback, for managing transactions, also in script 5. To illustrate SQL, imagine we have a customers table and an orders table. Using SQL, we can write a query to find, say, all customers who placed an order in the last week. This might involve a join between customers and orders and filtering by date. An example SQL query could be SELECT customers, name, customers, email from customers join orders on customers, customer ID equals orders, customer ID where orders, order date and GT equals 20250820. This query selects the name and email of all customers who have an order on or after the 20th of August 2025. Don't worry if you're not familiar with the SQL syntax yet. The point is that SQL provides a human-readable way to ask questions of the data. One reason SQL, and the relational model, became so popular is its strong foundation in set theory and logic. SQL operations like joins, filters, and aggregations, sum, AVG, etc., allow for powerful data analysis directly in the database. Another reason is standardization. SQL, with slight variations, is used in many database systems, meaning that learning SQL is a transferable skill. It's also worth noting that SQL isn't just for querying. You also use it to create schemas, define constraints, and more. For instance, to create the tables above, you'd execute SQL DDL statements to define each table's columns and data types, and maybe define primary key and foreign key constraints so the database knows how customers link to orders. To summarize, SQL is to relational databases what a steering wheel is to a car. It lets you control and use the power under the hood. It has become one of the most important languages in data management. 17, allowing users to retrieve exactly the information they need out of potentially huge datasets efficiently. Transition. Now, SQL rose to prominence with relational databases. But in recent years, you've probably heard of NoSQL databases as alternatives. Let's clarify how SQL databases compare to NoSQL. SQL versus NoSQL. The term NoSQL covers a variety of non-relational database technologies, as we touched on earlier. Let's compare SQL databases, relational, with NoSQL databases, non-relational, on a few key points. Data structure and AMP. Schema. SQL databases use a fixed schema, tables with predefined columns and types. Data must fit this structure. Every record has the same columns. This enforces consistency and is ideal for structured data. NoSQL databases, on the other hand, often have a dynamic or flexible schema. 18. For example, in a document DB like MongoDB, one document might have fields that another doesn't. NoSQL models can be document-oriented, key-value, column family, or graph-based instead of strict tables. 19. This flexibility makes NoSQL attractive for scenarios where data formats evolve or vary, e.g., log data, user profiles with varying attributes. Relationships. SQL databases explicitly support relationships via foreign keys and join operations, hence, relational, DB. NoSQL databases typically denormalize data, embed related data together, or handle relationships differently. Graph DBs excel at relationships, but key-value stores might not directly support relational joins. If complex join queries are required, SQL databases usually make that easier with one query. In some NoSQL systems, you may have to handle relationships at the application level or use specialized structures. Query language. SQL databases use, of course, SQL, a standardized query language that is quite powerful for analytics and reporting. NoSQL databases do not use SQL, though some have SQL-like query capabilities. Instead, each has its own way to query. E.g., MongoDB uses a JSON-based query language. Cassandra uses CQL, which is SQL-like for a column store. Neo4j, a GraphDB, uses Cypher query language, etc. Some NoSQL databases, especially simple key-value stores, might not even have a robust query language. You retrieve by key or do simple pattern matches. So in terms of ease of querying, SQL has an advantage for complex queries, whereas NoSQL may require more work for complex filtering unless you use a tool suited to that data model, for example, Graph queries in Cipher can be more intuitive than SQL for traversing networks. Scalability. This is a big differentiator often cited. Traditional SQL databases are typically vertically scalable, meaning to handle more load, you would use a bigger, more powerful server. Scale up, 2021. There are clustering solutions, e.g., distributed SQL databases, or sharding techniques, but generally the model is not as straightforward to distribute across many nodes because of the strong consistency and join logic. NoSQL databases, in contrast, are often horizontally scalable. They are designed to run on clusters of commodity servers, scaling out by adding more machines. 23. For example, Cassandra or MongoDB can partition data across many servers automatically. This horizontal scaling is useful for very large datasets or very high-throughput applications. Think of Facebook or Google Scale, and is a reason many NoSQL solutions were adopted by web-scale companies. Consistency and transactions. Most SQL databases follow ACID properties for transactions: atomicity, consistency, isolation, durability, which ensures strong consistency. Once a transaction is committed, all reads will see the same data. Many NoSQL databases relax some of these guarantees, favoring the AP side of the CAP theorem, availability and partition tolerance over strong consistency. Some NoSQL systems are eventually consistent, meaning data will become consistent over time, but reads in the short term might see stale data. This is a trade-off to achieve better distribution and uptime. However, it's worth noting that newer NoSQL databases and distributed SQL databases have blurred this distinction, and some NoSQL can be configured for strong consistency too. But as a general contrast, SQL equals strong consistency, schema enforcement. NoSQL equals eventual or tunable consistency, schema flexibility. Use cases. SQL databases are often best for structured data and complex queries, for example, banking systems, ERP, CRM, where the structure is well defined and transactions must be absolutely reliable. NoSQL shines in use cases like big data analytics, where you might use a columnar NoSQL store, real-time web applications with massive scale, where you need to distribute data across many servers easily, or situations with unstructured data, like storing JSON documents with varying fields, or social network relationships which are graphy in nature. To sum up the comparison, SQL databases, relational, provide a mature, consistent, and powerful way to store structured data with the ability to use SQL for complex queries and ensure data integrity, through schemas and constraints. NoSQL databases offer flexibility in data storage and high scalability, handling data types that don't fit neatly into tables, but often at the cost of the rigid guarantees and sometimes the rich querying that SQL provides. Both SQL and NoSQL have their place, and in fact many organizations use them side by side for different purposes. Some systems even integrate both, so-called new SQL, or multi-model databases that can do documents and SQL, etc. The key takeaway: use SQL, relational, when your data is highly structured, requires multi-row transactions or complex joins, and fits on a single, or modest number of, servers. Use NoSQL when you anticipate a need to scale out massively or your data is heterogeneous, or your access patterns are simple, key lookups, etc., but at huge volume. 24:18. Call to action smiley face. That wraps up our overview of data models and SQL fundamentals. You've learned how data can be modeled hierarchically, in networks, relationally, or in newer NoSQL forms, and why SQL is such a powerful tool for interacting with relational data. If you're enjoying this deep dive into database concepts, make sure to subscribe to DSN and hit the notification bell. In the next lesson, we'll dig into core SQL concepts like data types, integrity constraints, and operators essential knowledge for actually designing and querying databases. Give this video a like if you found it helpful, and as always, drop any questions in the comments.